Hello again, and we're carrying on with this introductory part of Math 2005. So last time we were on this slide, just giving an overview of the structure of the module for this term. And now I want to say some sort of points about how we approach learning about numerics. The first thing is it's helpful just to stand back at this stage, just to have a think about how we actually learn about numerical methods. And this is a reasonably practical mathematical topic, and it also involves computer programming in the sense that it uses computer programming. And I would suggest that you approach it from 2 or 3 different aspects, and when you do that you get a really rounded approach, and hopefully through this module, this term, you'll see that those different approaches in action. And those different approaches are firstly used analytically, which is closest to other modules you'll be doing, whether it be analysing the convergence properties of different methods, and we'll be doing that with in different contexts throughout. And those are in lectures and tutorials classes. You can actually solve your numerical methods by hand. Some of you would have done Newton-Raphson at A level, say, by hand. And that's fine for understanding how things work, but you ultimately will need to do some programming beyond a certain stage. And these were in the lectures and problems classes. And then at a computer using MATLAB. And this will be in the practicals. So there's 5 practicals in this module. This year I'm introducing something called live scripts, which combine the theory and the code into one little document in MATLAB, and we'll be using those. And this is really quite important to sort of develop your programming abilities. Now, you may have had different views on MATLAB in the year 1, but I encourage you to sort of stick with it this year. We'll do a refresher course in the first practical, and if you try and avoid MATLAB altogether, well, you won't be able to, I don't think, for the coursework. So it's an integral part of the module. It's a programming module. And finally, there's intuitively using diagrams, and you'll see lots of diagrams in the notes online. And I direct you to my notes. I put all the notes for this module that you'll be examined on into next term, and the first 4 weeks of next term. So everything's there in front of you and in LaTeX. And do point out to me any errors you find, and I'll update the notes as soon as I can. There's sort of a living document in some ways. So let's just see why we need numerics. Okay, so hey, let's go to the board for this bit if we can. Here we go. Okay, so if we have the integral between 1 and 0 x squared dx, right? We know how to do that. Let's just solve it. Let's just solve something easy. You've done that at A level. So that's x cubed over 3 between 1 and 0. And it's a third. Easy. Yeah? But, that's a smiley face. But, what about this one? Which is the integral from 2 to 1 of x to the power of x dx. So just seemingly a subtle change where you put x in the numerator. And the point is with this is that we need numerics. I mean, we can plot using a computer y. So if we plot x to the x, it kind of looks like that. That's y equals x to the x, and we can see that between 1 and 2 that the integral exists, because it's the but we need numerics to solve it. So we've got that area under the curve there. You can see it exists. We're going to need numerics to solve it. So that's just sort of a simple example where numerics is important. So then coming back to our notes here. So the other thing is he's using MATLAB. So let me just, whilst I'm talking, get my MATLAB loaded. So I'm using 2020 version. And I just want to take you through some very basic commands that we'll be using again in MATLAB, and to realize that you know, that's what we're about. I want to make the point that so I'm going to just bring it over here and use the command line here. Don't worry about the code up above, that's just a bit of code from my research. I'll hide that away. There's no secret about that. So there's command line here, and I'm just going to punch in some simple commands. So last year you should have been doing some programming with John Thuban. This year we're using the MATLAB. It's really to support our understanding of the theory. So it's using it in a reasonably similar way, but we're not doing programming per se. Now, if you need help catching up, we can try and discuss that in some of the live sessions. But really, I'm trying to use the codes to support the thing. So for that reason, I often give you templates, or actually these live script books, live scripts with everything set up. You only have to modify a few bits. Whilst in the coursework, obviously, I expect a little bit more programming to be applied, but it's really trying to use the code to understand the theory rather than doing programming necessary for its own sake. And that, in many ways, that's how we in the mathematics degree use programming a lot of the time. But anyway, let's look at an example. So if we want to put in a matrix, now MATLAB, I don't know if you've been explained this, but the origin of the word of that programming language is mat means from matrix, lab means laboratory, and going back probably 20 years, maybe more, there's this old language which still exists for a lot of big codes called Fortran, and had a lot of different packages there, but it was not very user friendly for people learning languages, really. So someone wrote this thing called MATLAB that really combined all the matrix functionality of Fortran into a nice unit. So doing matrix stuff is really easy, and it's really where MATLAB shines over other languages. So that's section 3 of this module in particular, but other places are helpful. So I'm just going to show you how to put in a matrix. We're going to put a 3 by 3 matrix. So the first row is 1, 3, 2, and we put in there's different ways of doing this, but I'm just going to put a semicolon, separating the rows out. So 7 minus 1, 2, 5, 4. And if you're struggling with confidence with MATLAB, I wouldn't say try to write a big program and get it working. Try doing commands at the command line like this and see what happens. You know, there's a very helpful thing in the top corner of MATLAB that's this when there's cursors on it there, this question mark helps, and actually that's there, that can help you with any sort of command in MATLAB, so do take advantage of that if you need it too. Okay, so that puts in a 3 by 3 matrix, and voila. And if you want to do a vector now, so this is a column vector I'm going to put in. And this little colon rather, means transpose. So this gives you a column vector 5, 7, 8. Now just see how easy MATLAB is for doing matrix stuff. If you want to find the eigenvalues of A, just do A, eig of A. If you want to do the transpose of A, just do A inverted comma, and it'll give you the transpose. If you want to find the inverse of A, just do inv of A, and there it goes. So it's very good for this, and we will be drawing on it as we go forward. Okay, so more to come of that. So I hope that just gives you sort of a approach of our philosophy for this module. And as I say, any problems with the programming side, you come to me. Hopefully the practical live sessions will help with that. Talking about key concepts, another key concept in this module is iteration and convergence. Really, that's what all the methods are about. It's about making a method, whether it be solving a matrix problem, whether it be solving an optimization problem, where it be solving, and then where we can iterate, i.e. repeat, in a loop or in a while loop, and come to converge to a solution. So, and this process is easy for computers in a way. You just tell them to do it many times, but it's very boring for human beings. So this is where computers come into known. And where the mathematics comes in a lot of the time then is analysis of the convergence. Understanding before we hit the computer, before we write code, that what the conditions of convergence are of the method that you're using. So that's really where the mathematics sort of earns its money, really. And the key idea is that it should converge to the true solution. Let me just try and let's get a new book. Okay, I'm just using a simple sketchbook here. Okay, so what we define a lot of the time in one dimensions is what's called the true solution, and we're going to call that x star, x subscript star for the true solution, and then the numerical solution at step n, and we're going to call x sub n. So hopefully this sort of notation might be familiar. But the idea of convergence in a line is essentially this, that xn tends to x star, the true solution, as n tends to infinity. Okay, so that's what we're looking for a numerical method. If it doesn't converge, it's a waste of time trying it in the first place. But this really is where the method, the mathematics, the analysis, if you like, numerical analysis is the underlying subject here we're doing more of, comes into its own. That we want to test convergence, that this thing is going to go to the true solution. Yeah. Okay. I just write up here Taylor series. Don't forget about your Taylor series. It's come up probably several times now in A-levels or last year. It really is a very useful thing because basically it's asking you where a function at a distant h from x can it be approximated. So it's got discretization in it. The whole idea of numerics is discretization, going discrete values of x. So if h is your discretization, then it's saying how does f vary away from it, and we can then make lots of inferences about the methods we're using this. So here, for example, if I just expand up to second order, I have this h f prime x plus h squared on 2 f double prime of x, and then you can put it through as a summation. Okay, so simple, but it will come up again in lots of different contexts. I'm just drawing attention to that bit of sort of knowledge from the past. Okay, so notation. So I've mentioned already this x sub n for the iterated value of x, where that's in your method, and will be typically represented by n or I in the subscript. So that's what we're looking for, and we're looking for that to converge to the true solution. The module is self-contained. The lecture notes should be self-contained. About 3 years ago, I bit the bullet and translated a whole bunch of written notes into LaTeX notes, which now they're there, are a lot easier to maintain and are hopefully a lot clearer to you. So use those, dig into those. If you find any errors, that's great. Come and tell me. I won't be sad, and I'll correct them. That shows you sort of reading them very critically. But the course itself is kind of inspired by a number of books, I would say, or one book in particular in the early sort of first 3 sections of this term inspired this module 10-12 years ago when it was written, and that's this one by Karab and Gunther, An Introduction to Numerical Methods, a MATLAB Approach, 3rd edition. So it follows the module, this term, quite closely and covers everything except 2D optimization. So if you want to sort of read around the subject a bit, I would suggest that, and talking to the library. If you want, just for interest, to see what the full canopy, if you like, the full picture of numerical methods is beyond this, just beyond this module, there's this thing called Numerical Recipes, which is kind of a classic, and you can see there it's got 1256 pages, and believe me, it's quite concise. It's just that there's a huge number of numerical methods out there used in science, and if you just want to get a flavour of where you can go with numerical methods, have a look at this, and it comes in all sorts of programming languages. I imagine it comes in MATLAB. I haven't checked recently, but it certainly comes in every language you can think of, have a look at that. Okay, so this concludes the sort of introduction section. Next time I will start root finding, so revisiting 3 root finding methods that you've come across before. Bisection, Newton-Raphson method, and so on and so forth, and but hopefully analysing it in a little bit more detail than you did last year. Looking at the convergence properties, and to see how we can apply our mathematics rigorously. You may have done a little bit of this with John, but we're going to go in a bit more detail here. And as I said, it's purposefully we're picking up on stuff you've done last year and sort of extending it to make it sort of a nice transition. And then we deal with the really new stuff in the second half of terms as well. Okay, so see you next time. Okay, bye for now.